So, hi, my name is Anne Albright. I am not Professor Koutromanos, who unfortunately was unable to present his presentation today. So I'm filling in on his behalf, but please grant me a bit of grace if I may not know everything, because I was not directly involved with much of this research. So as the title states, this presentation is going to be about seismic and damage analysis of reinforced concrete wall building systems using the BTM-Shell method. And this is a bit different from the other presentations in this session because we do not use machine learning directly. So just preface yourself for that, it's not coming. So for those who aren't familiar, reinforced concrete structural walls are very popular lateral force resisting systems used in existing buildings in earthquake-prone regions. The quantitative probabilistic seismic risk evaluation does typically require very extensive analysis of building systems. However, we think this can be a good candidate for data-driven and machine learning tools because of this high analysis required. The machine learning systems could potentially help offset those costs. As we all know, large machine learning models require extensive data sets of input and output to be trained on in the first place. And it's really quite impossible to conduct a number of large-scale experimental tests in order to calibrate these type of systems for large-scale dynamic systems, dynamic loading. And so I'm going to explain how the BTM-Shell method that we use in our research is accurate, computationally efficient analysis methods, which can produce a large data set to then hopefully in the future train machine learning algorithms. So here are some typical damage patterns in reinforced concrete walls. We have at the boundary regions, you get this toe crushing or bar buckling and followed by bar rupture. These are very typical failure mechanisms at the end regions of a wall. You can also get diagonal tension failures, which are very common, as shown in Wallace and Liu, and highlighted in the red lines here, as well as diagonal compression failures. These are some of the most typical types of failures of shear walls. So in terms of analysis of reinforced concrete walls, different analytical methods have been used in the past. Simplified beam-based methods, Bernoulli methods, numerically efficient and conceptually simple. However, they may not accurately really capture all of the damage models, especially those involving strength degradation due to our large inclined cracks, because they obviously start with the basic assumption that plane sections remain plane, and that's just simply not accurate in all cases. You can also use continuum finite element models, which provide insight at both the member level and the material response. However, these are very computationally expensive models, very, very computationally expensive, can be. So I'm going to talk about, and again, it may not even then accurately capture some of the damage modes that we're really interested in, like these diagonal inclined cracks. So I'm going to talk about the beam-truss model for RC walls, which was presented by Liu and Panayiotou in 2014. This method combines accuracy, conceptual simplicity, and computational efficiency. And the basic idea is that we are actually going to represent one of these elements in the wall model as a configuration of line elements. So we have horizontal, vertical, and inclined line elements. The horizontal elements and vertical elements are beams, beam models, while the diagonal elements are represented by truss elements. And the truss elements account for the compression field developing, like what happens in the wall web or what happens in the compression toe region. So here's an example of an RC wall component one engineer might want to build in your model. And this is how you might use the BTM-Shell elements to create this model. So looking a little bit closer, these vertical beam elements are fiber elements. So they have reinforced concrete, constitutive laws, and steel laws amassed in a fiber section model, which provides the through thickness flexural resistance. So this BTM method has been shown to capture all common types of failures in core walls. So I'm going to go through and show a little bit of those examples. But this is kind of the clever implementation. The whole point of the BTM-Shell model is that it does this 6-line element underneath what you can simply look at in a model as a 4-node shell element, which everyone knows you can just discretize your system, like Abacus or something can automatically discretize, which is really nice to see. But under the hood, you're getting a 6-line element. So these are our material models, constitutive models that are used in the analysis, as presented in other previously peer-reviewed papers. Confined concrete by Liu and Panayotto, which also takes into account the effects of transverse tension on the compressive stress, like in the modified compression field theory, everyone knows. And then the reinforcing model by Professor Koutramanos and Kim, also published. So this model can account for bar buckling as well as bar rupture, which is special, and that helps us capture the failure modes of these shear walls very well. So here are some examples of the validation analysis of the beam-truss model being used. This is a flexurally dominated response with strength degradation due to crushing at the confined boundaries. And the edges of these walls, they typically have these confined boundary regions with a lot of shear steel at those end regions, and normally a lot of flexural steel as well. You can see this wall is failing by crushing at the confined boundary region. And this is how our model predicted the specimen would fail, which you can see it has a very good capture of that crushing component, which can often be not captured in other models. Here's another one where this one had a flexurally dominated response, actually, with a bar rupture. Yeah, vertical bar rupture on this one and strength degradation. And again, the model was accurately able to capture that vertical bar rupture. When you look in the model and actually export the strain values, you can see that it captured that quite well. Here's another one. This is one of the diagonal tension failures that I was mentioning. It's also quite common in shear walls. And another wall tested by Wallace has another diagonal tension failure. And you can see that there's quite good agreement between our model and the experiment. And the failure modes are accurately getting captured in each of these separate conditions, which are often not easily captured by other modeling techniques. And we got one more. I'm going to go through these for time reasons. So in addition to these isolated walls, we can also model coupled walls. So the coupled wall in the simulation is when you have two large shear walls and then they have what's called coupling beams between them. And you can see that the test and the model, again, have quite good agreement. So we're showing the expansion of this program and this modeling concept to more than simply isolated shear walls. And even in blind prediction model, where there was a competition hosted at UC Louvain in Belgium, where they had you model two C-shaped wall specimens and then predict the outcome. And this competition was undertaken by three of our co-presenters on this presentation, and they actually won for both of these walls by using this BTM-Shell element. They were accurately able to predict a whole slew of things, from capacity to maximum strains, it was very impressive. They were very thrilled with those results. And then we can also extend this from beyond simply isolated walls and coupled walls into a full building system, which is what we really want to do, right? We ultimately want to be able to model our full structure and get an accurate representation. So this is going to be a model of a hypothetical 14-story core wall in downtown Los Angeles. And there was nonlinear static and dynamic analysis, which investigated the typical failure methods that were interested for shear walls, such as shear-flexure interaction. And we also want to see the damage patterns and the effect of triaxial earthquake excitation on this full building system. So here are some details. You can see it's two C-shaped coupled walls that we're modeling here, 14-story tall. Here's some parameters if you're interested. And this is the actual model. So this core is sitting in the middle of the entire building system here. So again, two C-shaped shear walls with coupled beams in between. We use BTM-Shell elements for the core wall slabs and coupling beams, and then beam elements with the fiber section for those columns. And also want to note that geometric nonlinearity, such as P delta effects, are captured in this model. And then it's really important to note that this model, what you're looking at in this graph here is the flange 2, I believe in this case, and it's showing the fibers in our beam elements, and it shows the strain profile along the full length of the wall. So the LF is the length of the flange, and you can just see that the strain profile changes and is certainly not linear. So this is just reinforcing again that plane sections don't always remain plane, and if you start with that assumption, then you can't expect to have a realistic model at the end of it. So this method of modeling captures the non-linear behavior that the plane sections do not remain plane. Oh, that's right there. So the dynamic analysis used triaxial ground motions from 11 previously recorded earthquakes. We have like an X and a Y on the ground plane, and then we have a vertical direction as well, scaled to match the maximum considered earthquake. Yep. So this should be the actual analysis. You can all see the video? Mm-hmm. Good. So yeah, what's important in this model to note is that in this corner where the red situation is developing is that the biaxial effects of both of those walls meeting at that corner is getting considered in this model. So that's really critical. So this is the global view of the model on the left, and then the bottom 5 stories of simply that core wall on the right. And you can see that ultimately what happens is that this corner crushes. That's the failure mode here. This is the time history analysis of the roof drift, and you can see in that bottom chord the maximum tension and the maximum compression as a plot over time. And what we want to note here is that the tension and compression getting captured independently is very important, because in the dynamic analysis results, this is at the maximum drift ratio in the X direction and the maximum drift ratio in the Y direction. The deformations due to the shear interaction here is actually a huge component when you separate the components of the overall deformation. The shear contributes over 50% or about 50% of the base deformation. And on the Y direction, it's actually even higher at 65% of the overall deformation is due to just the shear. So including the nonlinear shear interaction in your model is very important. And then also with that, back to that tension and compression chord, maybe I should have switched those slides, sorry. This is showing that the residual displacement of the structure can be very important when you're modeling, and being able to get an accurate representation of that can help determine whether or not you're able to repair the structure after all this damage has occurred, after your maximum considered earthquake. So now this is my this is my part. This is my PhD research that I'm actually working on. So this is an experimental test on a non-ductile wall. So this research is going on based on a older type of wall based on design codes from pre-1960s, where they didn't have as much requirements for your shear steel. So this wall is a half-scale specimen of an 8-story building, and it has very little reinforcing shear in the wall, and we've packed a lot more of that steel into those end regions, those boundary regions. And this was our experimental test result. And you can see the progressive damage pattern here. We ended up with a lot of diagonal cracks, and they just kept propagating up the wall. And then we had much more localized cracks, and these crack widths started opening more and more until eventually we ended up having a brittle toe failure at the end with a bunch of concrete crushing. So what happened is across this red line, the shear steel, the horizontal steel that we had in the wall, broke, and it could no longer carry that capacity. And so basically all of the force that the wall was trying to transfer got forced into the toe because that was the only load path left for it. And so we had a very explosive shear crushing failure. And then you can see that our analysis matched very, very well. You can see that the toe crushing is captured in this model. The localized diagonal cracking, which again we said the inclined cracks have been hard for other models to capture, was captured very well in our experiment, and it predicted similar drift ratios of failure. So here are just a couple more fun models to show again how validation of this method works for a large system level building. This is ongoing research. And the last one, the grand finale, this one is the full collapse of a 10-story building. Again, older building built from the 1950s under the maximum considered earthquake. This one, you can see the full progressive damage occurring after the shear walls. All right. So the concluding remarks I want to make are that this analysis approach, the BTM-Shell element, combines accuracy with computational efficiency. It can enable extensive parametric analysis of an entire structural system, not simply isolated walls or even coupled walls, but a full building system. It's very well tailored for shear flexure interaction for non-planar walls compared to other simplified analysis approaches. And it provides a unifying framework for simulation of both isolated walls and wall building systems, as we've talked about. And it's also very computationally efficient, which makes it a good candidate for machine learning algorithms, because you could produce a large data set of full building system models to then train data sets on. If you have any questions, I'm happy to take some, or you are more than welcome to email Professor Koutramanos at Virginia Tech.